so exoplanets part 2. We talked about how we've been finding them, so the planets are still really cool. We had these 5 different ways of detecting exoplanets around other stars, and they really only started happening because our cameras got good, right? So we can do things like transit and radial velocities and astrometry because our instruments got just that much better. And so you'll notice this in science, or even use this in real life. As soon as you've figured out how to do one, 1,000 is just cranking the handle. And so we've been cranking the handle since basically 1995. But the main thing that we've been doing is doing these transit methods where we can find a lot of information about the planets themselves, right? We've got the period, which means we've got the average distance. And if we can see how fast they transit across, we also get the ellipticity of the orbit. And so we get a lot of information, the size of the planets, the typical orbit. If we know the star's mass, for example, we also get the mass of the planet itself. We get the relative size, the width of the planet, the velocity. So we can get this, we get a lot of information. But now we're sort of in that next bit where we go, okay, if I know there's a transit, so if I've already confirmed that there's a planet there, I know that it's about the right size, it's about the right temperature, how far away is it from the star, and I know it's about the right density as well. There's a plot a little bit later. I now want to know if this is like Earth, and that's where it gets hard again, right? Because now, instead of just getting that transit, we now actually want to take a spectrum of that star as it's passing in front of it. So I showed you, this is what it looks like on Earth, and again, Earth is our template. That's the one that we want, right? We want to, NASA really wants to go out into the world and go like, we found a second Earth, and that to actually withstand peer review scrutiny. And that part is important because it's very easy, if you've got such a like holy grail kind of moment in science, like it's very easy to sort of delude yourself that you found something. And so it has to go through peer review. And I'm going to ask the room here, who has heard of the term peer review? Okay, most of you, do you know what it is? Yeah, okay, most of them. So just to reiterate, peer review means it's not a perfect system, but it is something that has sort of evolved after World War II in most sciences, that you take whatever people have published, right? They come up with like, before publication, they write a scientific paper, you give it to an anonymous other scientist that wasn't involved. Completely clean slate, you go see if you're convinced by this paper. And there's a whole bunch of things that you have to answer, things like, could you reproduce the experiment? Is that well enough described? Can you actually see what they did? Between what they did, what they're showing, are the conclusions valid? Like, do they actually back their conclusion? And so it's sort of the gold standard for like getting a scientific result out, but that doesn't mean that mistakes can still slip through. But that said, so this is the thing what we want to do. We want to see if we find an absorption spectrum, if we can see something like our Earth. And I found a better one. And so we want to basically want the Earth shine, like what comes off what we observe from our own Earth. And this is the kind of spectrum that we're seeing. So there's, here is the ozone. So that's again that we saw before, like here's ozone. So this is the light that comes back to you in space. That's one way to look at it. And that's one way that we want to, if we see a little blue marble somewhere, do we see these things? And so here's things like, vegetation makes an appearance. Here's all that water, here's oxygen, CO2, methane. Here's all these different molecules that play a role in life on Earth. If you don't think methane plays a role on life on Earth, well, it's the cow farts, right? It's all the flatulence it's basically decomposing vegetable matter. And so if you have a bunch of trees, you're also going to have methane, because if you don't have a life cycle, there's nothing decomposing, then you won't see any methane. Methane reacts pretty quickly with oxygen, so if I have an atmosphere that has methane and oxygen in it, it dissipates, like the methane will react with the oxygen and will end up as CO2. So you have to have constant production of methane in order to see it in an atmosphere. There's many different ways that you can make methane, and not all of them involve cows or decomposing grass or something, right? There's very different ways to do it. Volcanoes are a good way to do this as well. So it's not a clear-cut piece of evidence, but if you start seeing things like, here's the effect of vegetation as well, like chlorophyll, we're now feeling very much comfortable saying that this has some plant life on it. Okay, and as we're starting to think about this, we say, like, we want to see a second Earth. And I really love this plot. Like, somebody lovingly put this together, because which Earth are you talking about? I had a bunch of dinosaur buddies here in the room. Well, is it the Archean Earth? Is it a Proterozoic Earth? Or is it more modern Earth? This gives you an idea of what the atmosphere was made of during the various, for the most recent billion years, the billion years before that, all the way up to like 4 billion years ago. So the Earth's surface has just cooled enough to have like liquid water. So as you can see, CH4, 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 and oh look, CH4. This was basically a methane atmosphere, and there was no ultraviolet getting to the surface because of all the haze, basically little particles that were left over from all the bombardment of the asteroids and early bits of planet that arrived, essentially. So you have a very different atmosphere than you have down here. Completely different composition, so lots of methane and carbon dioxide, and then plant life starts to kick in, and we actually sequester a whole bunch of that carbon dioxide into trees, ferns, that kind of thing, and they get subsumed into the Earth's mantle, and oxygen basically pops up all back here. Ozone pops up here, oxygen basically pops up here. So this is a very different atmosphere from the Archean Earth to Proterozoic Earth. This we could breathe, and we would be mostly okay, probably wear sunscreen. But it would be, if you're a time traveler, like, do not go back further than 2.5 billion years. After that, it just gets, it's worse than LA smog. So don't go there. And so it's which atmosphere do you plan to, or which atmosphere do you expect to see? And so, yeah, there's water the whole time. There's water vapor, but it switches in the amount quite rapidly and quite dramatically if you consider that this is the entire lifetime of the planet. So you might just catch the very early Earth, and you go like, oh, this is fantastic. I can actually see a very early Earth, and it must have just formed. So it's not necessarily that if you find a modern Earth equivalent, or maybe we find a Proterozoic Earth equivalent. So there's a component of like, well, how convincing is it? Meanwhile, our artists are hard at work, knowing, like, sort of interpreting and thinking what those planets would look like. And then you have that part with like, yeah, it has to be the right distance from the parent star, right, the habitable zone, or at least the liquid water. We did this already, so yes. We have relative sizes of some of the habitable zone planets, right? So these things some of them are quite a bit bigger than our Earth, but they're big enough to have liquid water. I told you that TESS is currently looking for nearby planets, and our telescope here at Louisville is busy following up whenever TESS finds a little dip, and it has moved on to the next sector. We will follow it up with this telescope and actually see if there's another dip there confirmed. We talked about the absolutely gigantic telescopes that we're now building to get the atmosphere. I showed you this one already, but yeah, we're having plenty of the ones that are essentially close to their parent stars and are, Earth mass size. There's enough of those. So we have plenty of real estate, and so we want to go see if we can get these spectra. And the very first experiments were done with the Hubble Space Telescope and the Spitzer Space Telescope. Spitzer has been retired in the meantime. It was trailing our orbit so far that we actually had to start looking around the sun to get talk to it. And so what we're trying to do is the combined spectrum of the planet and the star, and then as it's moving behind, we get just the star, so we subtract that, and then hopefully we're left with a planetary spectrum. So what's, the Earth shine, that's the kind of thing that we're hoping for. And the thing is, we're trying not to get something that is, or we're hoping for something that isn't just methane, right? If I take Titan, for example, it's methane, 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 and oh look, more methane. But if I get something that has ozone, oxygen, water, carbon dioxide, and methane, so all these components, then it has either volcanism or plant life or both. And so those are the things that we may want to look at in detail. I always try to have some what's the latest? Well, this was last week. This is a direct imaging of the James Webb Space Telescope of 4 planets around HR 8799. So we're starting to actually get direct pictures of them. And look, they're not the same color. There's a blue one over here, you can barely see it, but it is, we're getting some first indications of what these things, like we're hoping for an optically blue one, right? We're hoping for a blue marble, maybe a blue-green one. That would be fantastic. But James Webb is mostly for that spectroscopy, and so what we found is the effect of carbon dioxide on one of them, and so there's a lot of carbon dioxide and carbon monoxide in that particular. This is what you expect from the star, and then this is what we're actually observed. And so we think that this one of these planets has a lot of carbon dioxide. It's a giant gas planet, but it is mostly made out of carbon dioxide. One more thing that was last week. This is the nearby stars. We talked about it when we talked about this is the life of stars. So this is the sun, and this is 15 light years away. Here is Barnard's star, and I always have to go figure out which point it actually is. Oh, it's here. So it's within 10 light years. Barnard's star was one of the ones that was looked at, and it also now has been found to have planets. Every time we keep looking at a star in detail, it turns out to have planets. And once again, the resident artist at NASA went obligingly nuts and actually made the 4-planet system. So we keep finding these multiple planets, multiple rocky planets. So TRAPPIST is currently still the record holder with 7 of them, 3 of which are in the habitable-ish zone so essentially not too warm, not too cold. Showed you this mesmerizing orrery. And so it all comes down to how far away you are, right? So we've had this part when we did distances. Every time you double the distance, so if I go twice as far away, I have to smear the light out over 4 times as much, right? This is the R² law, and so every time I go further away, I get less light from my parent star. So if I put a planet here, I get 1 unit of energy, but if I put my planet here, I only get 1/4 of that, and if I put it over here, I get 1/9 of that. So there's an optimal part where I receive enough energy from the parent star. So we can figure out if we know how hot the parent star is. Oh, we do, right? From the black body radiation. Then we know how much, and we know how far the planet typically is, again from this period. Then we know how much energy it's getting. So we know it's rough temperature. And so that's how we get the habitable zone, right? It's too hot, just right, or too cold. And it is a little fuzzy on the edges. And why is it so fuzzy on the edges? We'll talk about that when we talk about the rocky planets of our solar system next week. But the real thing is, it makes a big difference if you have an atmosphere. Because if you're just a bare rock, you're going to be this temperature because you've got this much energy coming in and you radiate it away into space. That's simple. That we can understand. If you have a bit of an atmosphere, you catch some of that heat and you don't transmit it out into space as easily. So, greenhouse effect, the greenhouse effect. Essentially, if I put an atmosphere on it, I get a greenhouse effect, and I can retain the heat. So I can be too cold if I were a bare rock, but if I've got a nice dense atmosphere, I can retain the heat enough to actually be warm enough for liquid water. This is why this is a little fuzzy. If I've got nice enough high cloud cover, I reflect enough of the sunlight high up so that I don't actually get enough of that heat. So actually I can be cool enough for liquid water. it does make a huge difference if this thing rotates or not. If you're tidally locked and just one side is getting baked and the other side freezes, neither of them are going to be very good for liquid water. But if I then have lots of circulation in my atmosphere, basically a constant tornado going around, then I actually might be cool enough. So this is a whole debate. This is a whole thing that we're trying to figure out. But this is also the reason that Venus is habitable-ish. I mean, in its past, it may have been cool enough to actually have liquid water. We don't quite know. In the past, Mars is very likely have been warm enough to actually have liquid water. But Earth is currently the only one that has managed to do it for the entire lifetime. So, to mess with an astronomer, put a mirror in front of their telescope, say, oh, I've discovered an Earth-sized planet with stars in a habitable zone, and even have oceans and a visible weather. So it's like, great, that's actually what we were trying to go for, right? We want to take a picture like that. This is still an artist's impression. We want to get a blue dot picture, like we've got from the moon. So we really have to up our game telescope-wise. So we have many that have now been found near or in the habitable zones of the parent stars, but there's still limitations. Centauri and Gliese, these are other examples where it's like, yeah, it could be liquid water, so we draw liquid water immediately. Or, for example, we find, and so we're still trying to get the composition from these stars, but sometimes we find a really strange star to even have planets. This is the oldest star with planets. The star itself is 11.2 billion years old. That's almost as old as the universe being 13.6 billion years old. And it doesn't have a lot of metals, right? This is the very first generation of probably still first, maybe second generation of stars. And so you don't have a lot of silicate, you don't have a lot of oxygen, you don't have a lot of carbon in the universe. How on Earth, or better, how on Kepler 4444 did you manage to get a planetary system around it? But it's there. So apparently this is very easy to do. Making planets, making other worlds is quite straightforward. I have to do the habitable zone picture. You know, this is why you should think of it, the optimal place to roast marshmallows. Not too far, not too close. Because if you get too close, stuff like this happens, right? So we have an exoplanet with an evaporating atmosphere. Some of them are so close they are literally losing their atmosphere, and we can see that because they transit, and we still see a trail of molecules in the spectrum of that star. So it's actually trailing, it's evaporating before our eyes. So it's also not unthinkable that it's actually straightforward to destroy planets. They can lose their orbit enough that they actually spiral into their suns. They can freeze. It's an inhospitable universe out there. You could kill your whole planet. So the thing that we're interested in is mass, how heavy it is. We get that from the Parkinson period, and how heavy the parent star is, and the radius. We get that from the transit. And if I now look at that a little bit closer, and so we find a whole bunch of these. This is already a slightly older plot, but this is a solid metal ball, and this is a solid water. This H2O. It's a solid ball of water, and the majority of the ones that we are finding are sort of in between those. So they could have an iron core like our Earth has, with lots of water. So the density is about right. If I get the radius and I get the mass, I can figure out what average density these things have. It's a ball. You figure out the volume from the radius, and then it's like, this is the mass, okay? And they're all sort of ish, like some are less dense than a metal ball, not quite a solid blob of water either. So they all look like terrestrial planets. So plenty of real estate at the right distances, with water implied at the right density. So this is great for life on Earth as we know it here. If we plunk a bunch of Earth species on these planets, maybe quite a number might survive, right? This seems doable. We could go there and raise chickens. This is possible, right? Okay, so we know that this is good for our life on Earth. And so this is where I introduced the Drake equation, and the idea for this is it's a ballpark estimate. I put all the slides on Blackboard so you can have a look later. So we want to know, for example, this is if I have a radio telescope, nobody wants to have that thing sitting idle. So if I want to go search for aliens elsewhere, right? I want to search for extraterrestrial intelligence. Yes? No? Nobody wants to do that with me? All right, so some of you are on board. Okay. If I want to know that, I want to know how many of those, of all the stars that I can see, and know that there are, how many could actually give me a radio communication, a Wi-Fi signal, you name it. Okay, well, what I do is I take the average rate of new stars, the fraction of those that have planets, and then the number of planets, the average number of planets in each solar system. The fraction of those that can actually support life, right? So quite a number don't, but we have a few that could support life at some point. Fraction of those that could be intelligent life, so civilizations. And then the ones that are smart enough to actually invent radio. And so the ones that have a certain technological level, and then the length of those civilizations. The important part is that if I want to know the total number and I have a rate of new planets being made, I want to know how, if I make a new planetary system, how long do I get radio signals from that? So this is the part that can be a little depressing because there's about 50 years between us discovering big radio signals and sending them out in the universe and the atomic bomb, so there's not a ton of time before you have the ability to completely wipe out your civilization. On the other hand, you can also go, it was 100 years between inventing radio and inventing cable, and cable you don't project. So maybe we don't see them because they've moved on technologically, right? It's not actually a long technological phase. So what I want you to take away from it, though, is that when this was proposed by Drake, not that Drake, astronomer Drake, that all of these numbers were completely unknown. So you could fill in whatever you felt like in order to get the total number that you could talk to. So we have the number of stars produced per year, the fraction of stars that have planets, the number of planets per new system, the fraction of planets with life, the fraction of the civilization, the fraction, intelligence, civilization, and then the length of that civilization. Here's the fun part. This we now have constrained. We know how many stars are being formed in our Milky Way. We know how many of those have planets, all of them, so that fraction is basically 100%. And we know how many typically are formed per solar system, more than one, several in fact. And so now you're getting to be like, well, how many of those have life on them? So that's our next hurdle. If we find lots of rocky planets that have methane, oxygen, CO2, and maybe some ozone, and you kind of go like, wow, there's a lot going on, and maybe they have a green tinge, then you go, maybe those are all green planets, so they all have forests and plants on them, then this might creep to 1. Or maybe you never see that at all, and you go, we've only seen this on Earth and nowhere else, and this might creep to 0, at which point those don't really matter. So I have I have one.
There's some stuff in the podium all the way forward.
Yes. Okay, here it is. Sorry, I printed it on Tuesday because we're moving building again. So I have a little Drake equation. And so Drake equation is not an equation where you go, I'll fill in the values and then I know what the answer is, which is, I think, how you get a lot of equations in high school and elsewhere. A Drake equation is what you would call an estimate, right? You do, it's about this, it's about that. how many ballpark are we talking? And I'm sure the narrative of science that you've had so far didn't include, oh, scientists do a ballpark, but they absolutely do. This is called a Riemann conjecture. So you basically say, is n more than 1? Is it even worth looking if I just assume the usual assumptions? Or this is, I think, is reasonable. I should be seeing 100 of these things. Where is everybody? And so getting an estimate of how many radio signals you should be getting, and there's plenty around if anybody needs any more. I've got plenty. This is an idea of like, well, the Fermi paradox basically says, where is everyone? We don't hear anybody. We have not picked anything up. Are the distances too big? Do we all switch over from radio to Wi-Fi to cable? Or are we just unlucky? So we'll talk about that more on next week as well. Hey Drew, is it okay if I bring Milky Way bars next week? I'll do that.
Always.
Oh. I don't. Sorry.
Need something to write with?
Oh, I don't have a pen.
We have lots of them.
Oh, okay. Yes, lots of them get left.
A jar of pencils in there.
speeds is. All right, so last fun thing, this has nothing to do with, well, it has something to do, a lot to do with this, but the transit method got so good that we started noticing other things there as well. And you know, when you say exomoons, you have to make this joke basically that you say that's no moon, but we can find rings and exomoons this way as well. So not only do you find the transit for the actual, so if you find the transit for the planet, right here, the planet is happening, but you see a little secondary transit here and not here. So something's orbiting that planet. That makes a little divot here. You don't see it because it's now orbiting around, so now it's here, and now it's either in front of or in the back, so you don't actually see the transit now. So we're seeing the evidence, and so we actually found, for this Hubble follow-up, you see evidence for exomoons. So one of the questions that we have about our own Earth is a really big moon like that normal? Well, if we find lots of them, maybe you need one of those, right? You need a big moon around the rocky planet in order to catch some of the asteroids, maybe have tides so that this helps life on a rocky planet. Well, how common are big moons? We can actually start answering that question. Now, this is something that a friend of mine made, and I love this little visualization. He actually found a light curve, and it just kept going up and down, up and down. And he saw like all these different dips and going back up and back down. And so what he was trying to figure out was what that was. So we saw a background star, and what he thinks happened was this massive Saturnian system. So a Saturn, but even bigger, with all these different kind of rings, has essentially given us this absolutely bonkers light curve as it goes down and then goes back up, and then you see the rings again because you sort of skimmed across the outer set of rings here. And so, yeah, you see keep going up and down, but it has a very typical for a ring system. So not only do we see moons, we actually see rings as well. So Saturnian-like rings, so think moons that have broken up, or moons that may have still be forming, and those gaps also hint at, again, small moons around this planet. So this is sort of my hint that we are going to the planetarium. Because I didn't know I was competing against the Louisville game. That's what I'm wondering where everybody was. So, okay, now I know. This is two of the planets, two of the moons around Jupiter. And so the neat thing is that if you look at Galileo's original discovery, he actually found something very close to this, right? He found Jupiter, and he found like a little dot on that side, and then a little bit later he found Jupiter and the dot on the other side. Hey, that is orbiting that planet. So some things never change. And so now we can talk about the planetarium and actually look at the exoplanets. And after that, we're done. So, ready, Drew, or did I spring this too fast?
No, get there.
Okay. I'll move to that. Any questions about exoplanets, right? This is touching on the whole, are there aliens out there? Well, the first thing that we can actually do with scientific inquiry is, do they have anywhere to live? And the answer is very much yes, provided they, like, the floor is lava, they have lots of places to live. If they're okay with, if they're a little more finicky about their neighborhood, then even then, there's lots of places that have water, liquid water, the right temperatures. And so we keep trying to understand both stars and planets better. And if life is has as many prerequisites as we do, meaning that we have to have a geologically mostly stable, so not too much volcanoes, and there has to be a giant moon around it. Like even then, we can start figuring out how many hospitable places there would be. And so this is what the goal is, and this is what we've been working for like a couple of decades now. Okay.
stop the recording because the